good and bad on the National Institute of Technology, NIST's website. It may require some digging, but it is possible to figure out which hash functions are secure and which ones are not. But a lot of developers just assume they're all secure, and that is not true. Believe it or not, but progress has been made since the 80s. All right, so let's begin our journey towards saving a password in a database. So we're going to attack this in 3 steps. So level 1 is that they're basically trying to attack our web server. So that implies that, maybe they can test something like 1,000 passwords per second, right? So they're just hitting the web server with a bunch of passwords, trying to figure out what's going on. Level 2 is somebody stole our database. So that's a really bad one because database queries are, as you guys all know, really, really fast. And so then we can assume that they could actually be attempting like something in the realm of 10,000 to 100,000 passwords per second. So all of a sudden, brute forcing the password becomes a lot easier if you have a stolen database dump. And database dumps happen all the time, unfortunately. Partially because of developers like us who use production data in their development environment, and then they're not careful enough, and their laptop gets stolen, or they accidentally upload it to S3 or whatever, and all of a sudden their production data is out there in the wild. And then level 3 is actually insider threat. So this one, insider threat, is not really for the amount of possible passwords to attempt. That's more so about a developer who's on, Tinder. A developer at Tinder is like, finds their boyfriend on Tinder, and they're like, what the hell? And so they're trying to figure out their boyfriend's password so that they can ruin his life. And so, that should not be possible, right? You want, however you're saving the passwords, you want even the developers who work there to not be able to get the password. Does that make sense? All right. I'm glad we're all agreeing with each other. So let's run an experiment here. So we have a plain text password, which is 123456, which, God help us all, is actually the most common password in the world. And I believe it still is for years later. Which we can then run through a hash function. And I will explain later what PBKDF2 means. We'll kind of work our way up to that, but it's a hash function. Enough said. So together, that produces a hash, and that hash is then saved in the database. And speaking of 1, 2, 3, 4, 5, I believe, yes, even my own capstone group used 1, 2, 3, 4 as their passwords for their database seed. So I mean, it's just ingrained upon us as a society to use 1, 2, 3, 4 or some variation of that as password. This is fine, however, because this is just for seed files. So it's totally okay, actually, because it doesn't have to be secure if it's just for development. But it was still pretty funny. So getting back to it. So what do we do next? Now we have a password and we've saved it in the database. So we would compare them, right? We would compare the 2 password hashes to each other. And that is how we would figure out if somebody has input the right login information, right? So one is from when they signed up. They input their password and we hashed it and saved it. And the other one is from when they're logging in. They're inputting their username, their password, and then they're checking whether it's valid, and then they save it. And then you just compare that to what you already have in your database. I feel like I jumbled that one up a little bit. Does everybody understand? Like, that's how authentication works?
If I understand correctly, you're basically only comparing the hashes and never the actual passwords?
Yeah. So you never save the password, you only compare the hashes. And that is like, yeah, you boiled right down to the crux of it. So that is correct, right? You never save the plain text, only save. If you remember only one thing from this entire presentation, remember that. All right. So
Question, I'm sorry. We're also saving the hash of the username, essentially, not just the password.
Fantastic question. So no, the username is not really secret. So we don't tend to need to, usually the username also is like an email. And so we usually do end up saving that so that we can send them email confirmations or send them password resets. So we do need to save their email. So you don't need to hash the user email. A password by definition should be secret, right? And often in cryptography, it's even called just the secret, just to denote that that is what it is. It's supposed to be as secret as possible. So that's why you never want to log out a plain text password. You never want to, the only job of a password should be, once it hits the API, its number one job should just be to get hashed as fast as possible before you have the opportunity to mess up and log it out somewhere or save it in plain text or stick it in a Redis cache or something like that. But great question. All right, so step one then on this journey is, why don't we just hash the password and stick it in the database? So it's good. This is good. This is way better than saving it in plain text already. So we're already kind of like, 80% there. But there is a problem here, which is, if we looked at our three levels, they were, 1,000 guesses per second, like somebody getting 1,000 guesses per second, and certainly somebody getting 100,000 guesses per second is going to run into 1, 2, 3, 4, 5, 6 quite quickly, because it's not a very long password for the first off. And that's actually going to be a recurring theme in this talk, is that it's very, very hard to, as developers, to protect the users from bad passwords. And I'll say that a few more times before this talk is over. But we're already doing well, right? We're already kind of like stopping most people. But if somebody was trying to brute force this password and just guessing a bunch, basically, this is too fast. A hash function runs super, super fast. So we actually want to try to slow this down a little bit. So now I'm going to open this up to the floor. What is a good way of writing really slow code?
Async.
Async is interesting, but it's kind of a, how should I say? So it's a good guess, but and it's a good way to do things asynchronously, but not necessarily for this, because async in one way is actually there just to parallelize different tasks, and so that might actually allow you, I hate to say it, to perform more password guesses. So no, definitely not async.
Could be loops.
I think I heard two different things there. I heard loops and I heard something else, but I couldn't quite catch the other one.
Storing things in like temporary variables to pass them around.
Okay, that's fair enough. Like, so you're trying to like use a lot of like memory. So those are both good ways of actually doing it. So I can't believe we hit on both good answers immediately. So loops is actually correct. It's something that they all teach us not to do, but it turns out that if you loop something 70,000 times, it ends up taking a bit longer. And so the recommendation for how many loops you should do depends a little bit on which hash function you should use, but everybody has a general consensus that somewhere between 50 and 100,000 is a pretty good sweet spot for incurring enough work that it'll usually take, at least like half a second or something to perform the work. And so that's like a really easy way to do it. And there is actually a different one. Speaking of the memory, there is another hashing function which does allocate a certain amount of memory, and doing that allocation takes a little bit of time, and it adds time like that, right? And the reason we want to do this is really nice because, it should be kind of intuitively obvious, because if we can, if we can try 1,000 per second, if we could just make it slower down to even like to take like 10 milliseconds, that will slow us down to 10 password attempts per second, no matter what. And that is a lot slower. And so anybody trying to brute force that is going to have an issue. However, now that we've gotten it slower, we are once again faced with the fact that 12345 is a really shit password. And so what attackers will tend to do then is they'll create something called a table. One implementation is called a rainbow table, but it's basically they'll be like, oh, I can see how they're hashing this. Certainly an insider would be able to look at this, and they'll be like, oh, I can see how this is being hashed. I am just going to generate a database with all the most common guesses, and I'm going to, attack that. So the next thing you can do then is you can use something, and doing that, it allows you to crack people's passwords very quickly, right? Because all of a sudden you can compare the hashes and be like, look, my hash for 123456 is one of the top ones, and so, ta-da, I got you. Does that make sense? They just make a database and then they just compare the two against each other. A database of common guesses using the same hashing algorithm that your system used. So they can generate that overnight or whatever. And so it's more so something that you'd probably use against a leaked database, more so than one that still lives on the web server. But yeah. So what can we do to prevent this? And I don't know, does anybody know? This one's a little bit trickier. The answer, if you will. It has something to do with spices.
Add salt.
Yes, there it is. That's right. So you can salt your passwords. And so this one is a little bit trickier to explain, and so I'm going to bring in some visual aids on the next slide. But roughly speaking, you just keep adding, you add a salt, which does not have to be a secret. In fact, it can't be a secret because you're going to need it when somebody tries to log in to perform the same hashing actions again and get the user's password to compare your hash to the hash that is in the database. So a salt is simply some randomly generated characters that you just add, like literally add, like a string add. Like this is the password plus this random string I generated, which is a salt, and I just add them together and then I hash that instead. And that way it'll just take whatever bad password you had and it'll make it look not like somebody else's bad password, because your salt and the other person's salt will be different because it's randomly generated for each different user. Every user has their different unique salt, which, by the way, is a very common error that developers make, is they give the same salt to multiple different people. Do not do this. If you're ever thinking about doing this, call me and I will tell you not to. So that is a salt, and it's a little bit hard to understand, and so I'm therefore going to show you an example, a very low resolution example. So here are the two people, and they have the same password. Their password is Bob. And in the first case to the left, there's no salt, right? There's no added random string per user added to it. And so their hashes look the same. And that's really bad, right? Because that means if I look at a database and I see that multiple of the hashed password values there are the same, then all of a sudden I, as an attacker, am probably like, that's probably one of the common passwords because these two people, have the same one. And so that already gives me a lot of information about, these guys using the same password. I'm just going to, these are the accounts I should be hitting right now for their financial info. Because, if they use that password here, they're probably using that shitty password somewhere else. And then, the whole shebang comes falling down. Now, on the right, though, we have with a salt. So ET52ED and YE5SF8. And because of that, the thing we end up hashing for the super smiling user is ET552ED and plus Bob, and then YE5SS8 plus Bob for the other user. And therefore, their password hashes in the database look completely different. And that is really, everybody always overcomplicates salt, but that is really what a salt is. That's all it does. Just add a little something to make people with shitty passwords have less crappy, not look the same in the database. That's really all salting does. And I added these. I didn't understand why they use happy smiley faces for the two on the left, because, they're both completely screwed. So if we don't, however, create a unique salt per user, which again is a mistake a lot of people do, then of course Bob AD245K and Bob AD245K is the same. And so it'll still look the same. And this is why you really, really need to generate and have unique salts per user in your database.
Chris, do we end up then storing the salts under that user as well, so that when they go and enter the password, we know to add the same salt to it?
Yes, you need to store the salt on the user as well, because you're going to need it when they try to log in. So you generate their salt when they're signing up and when you're first adding the data, or when you're first adding the password to the database, and then you use that salt anytime they try to log in to perform the same hashing action again, so that you can compare what was input by the user to compare it to what you have in your database. So the salt is the salt is not a secret. It can be saved alongside the user in plain text.
If we have a function for a user to reset their password, do you generally set a new salt then, or you use the same one?
That's actually a fantastic question that I haven't gotten before. I usually set a new one. I usually generate a new salt for the user at that point. But I don't really see a security risk with reusing the salt. I don't think it would be a security risk to reuse the salt, actually. There's no reason not to regenerate it, but it should be fine to keep reusing that salt for the user. But yeah, cool. I don't want to swear by that one though, but I can't think offhandedly of any reason why it would be a serious security risk. If your database leaks, it's probably a good idea to go through the salts again or something like that, but it should be okay. Good question. So,
Chris, I have a question.
Yeah, go ahead. Sorry.
Could we use the username as the salt?
It's usually a little bit short. Usually people tend to recommend using like at least 64 characters for salts. But because people would have different usernames. If usernames are unique, like I wouldn't recommend it. But that would still be a better idea than using the same salt for everybody. It wouldn't be a bad idea, but there's no real reason to do that. So I wouldn't recommend it. But yes, theoretically, if usernames are unique, you could theoretically do it. If you ever allow people to change their usernames, all of a sudden those users won't be able to log in anymore because the old salt will be gone. So, I wouldn't recommend it, but from a theoretical perspective, yes, that could be okay. But it's not a good idea, but it could be okay. All right. So now that we've kind of
Sorry, I have a question. Yeah, you said you store also the salt in the database, but if there is a leak in the database and someone sees the salt as well as the user password, isn't it like a way to go back to the password again?
So yes, the salt, you're completely correct, right? Seeing the salt doesn't really help an attacker very much. What the salt is there to prevent is to prevent somebody else generating a rainbow table, a table of lookups of common passwords to break you. But as is a recurring theme, there's very few things that developers can do to save you if you're, real Donald Trump at whitehouse.gov, right? If that's the user account that you see in there, that's the username, then that's probably the one they're going to be attacking. And so if that user has a bad password, and so you generate a lookup table just for that user. So imagine we're trying to, this is actually really important. So imagine we're trying to crack just one username, the president, in this database leak that's happened from the White House, right? We want his password. Then we can still generate the table because we have the salt, as you mentioned, and we know what hashing function they're using, generally speaking. And so we can just be like, look at all the common passwords and generate a table incorporating just that user's salt, Donald Trump's salt. And so that'll give you a lookup table that you can run against that particular account. And so that will work well. The reason to have salt is because now you have to generate one whole database just to look at one user. Before the salt, you just had to generate one database to look at all the users. But now you have to generate one whole database per user instead. And that's because of the salt. So it makes database table attacks a lot less feasible. It makes it a lot harder for the attacker to use. Does that make sense? So instead of generating 1 gigabyte of lookups, you have to generate, if there's 500 users, you have to generate 500 gigabytes. And as you know, looking through and parsing through 500 gigabytes is no small task for a computer. Even like, unless you're China and have a supercomputer at your disposal. And, versus supercomputers, anything we do as developers is going to be tricky. That's like a different level of adversary. A lot of my tips here are not going to work very well versus a supercomputer. But they'll certainly work a lot better than if you didn't do it. Does that answer your question?
Yes, it did.
Awesome. All right. So I told you before that we'd be getting back to PBKDF2. And so now you can kind of see what that actually is. So when we call PBKDF2 synchronously to hash a password, this is a way of hashing a password, you now understand why we're passing in all of these input parameters that we defined, right? First, we need the user's basic password, and then we need a salt so that, to prevent lookup attacks. Then we need the number of iterations to slow it down. Then we need how long of a hash we're looking to get out. So you can look it up, but usually people recommend grabbing like 64 or so. You want enough that there's no risk of collision. Like if you run it twice and it produces the same result. But if you're cutting it off too much, like if you're just grabbing like the first character, then, you're probably, there's only so many letters in the alphabet, so to speak. So eventually you're going to have a collision. And then what chosen hash function you want to use. For example, SHA-256, which I believe stands for like standard hash algorithm or something. And so that's one of the NIST standard hashing algorithms. All right. Algorithms. All right. So, and I have actually on my GIF on GitHub, I have a saving password assignment that you could look at and walk through. Alejandro did it 3 years ago. And it's good. It helps, it really walks you through these like saving a password, and it'll help you internalize this if you want. And I'll definitely throw this presentation into the Slack afterwards. So take a minute and read this comic. All right. All right, hopefully everybody's just about done there. So what is really wrong about this comic, right? So if you can build the feature that is in this comic, like knowing what you guys now know about hash functions, and how about if you just change one single character, everything changes. If you're saving passwords properly in your database, this feature here of like almost guessing a password should be absolutely impossible. It should be absolutely impossible to do this. If this is a possibility of like having this feature on any stack you're working on in the future, then that is a very, very bad sign. Like if you were like, oh, we could probably do this, and that's like, no. Yeah, this should be very, very impossible for any company, Twitter, what have you, to implement. So that said, that is how you save passwords. So now we're kind of moving into more so the important part of this talk, honestly.
Chris, I have a question.
Sure.
I remember some websites in the past when they'll tell me that I had the wrong password. Now most websites tell me either the password or my email is wrong. Is there any reason for that? Like, seems like before it would be able to tell me if my username was correct in a way by telling me that only my password was wrong. But I don't know if there's anything behind that.
Sure. No, there absolutely is. So that comes down to a lot of websites try to not give away usernames unnecessarily as well, because if an attacker knows that your user exists on the platform, then if they control the email, then they can certainly just reset the password back to you. So theoretically, you could imagine me writing a script going to all the financial institutions because I'm looking to steal money. And so I write a script that hits the login page on a bunch of financial institutions and says, hey, try to log in as this user, but I don't really care about the password. Just use password 123456. Honestly, I'd probably succeed on logging in a fair amount of time, unfortunately. But anyway, if I get back responses then that says this user exists on this platform, then I can take that knowledge and be like, oh, okay, so now I'm going to try to like just crack this user's. Now I know the user, and so now I'm going to crack the password. Or if I control the email, I can use the forgot password feature to go to that website and take them out. And so if you can hide that the user even exists on your platform, then that is technically a good idea, I would say. Although some other developers argue against me there because they're arguing that usability is more important. So it's a judgment call, but yeah. So that is why. So symmetric encryption, the James Bond of encryption, because this is what everybody imagines when they think of encryption. So this is not one directional. This is where it goes in two very specific directions. And so unlike a hashing function, we input two things. We input a message that we want to encrypt, and then we input a key. So it's like a password, but it's a key instead, right? It's a secret, if you will. And we input that through a cipher, and it once again produces some gobbledygook, which is my technical term for a ciphertext. And AES stands for the Advanced Encryption Standard. Once again, that is from NIST. And so this is commonly used when passing secret messages, for example. So I want to tell a secret to Alejandro, but I have to say it on live Zoom, right? Profess my love or what have you. And so I need to like encrypt that in a way where I can pass it to him with all of you others seeing it. And he is still, because he's the only person that knows the password, he's the only one who's going to be able to decrypt it and actually read the message. So unlike hashing functions, as I mentioned, it's reversible, but it does require me and Alejandro to have the same key. And so what a lot of people do then, because sharing that key is an issue, it's actually even called the key sharing problem. So you'll see that a lot online. So what people will do then is they'll usually, there's a couple of strategies, right? One is I find out where Alejandro lives and I go there and I give him the key out of band, or maybe like I figure out his, we give each other our phone numbers. And so we pass the ciphertext message over Zoom, but I text him in secret the key. And that way, so we go out of band, right? We use two different bands for the text and the key. So that's one way of, trying to improve the situation a little bit and maintaining secrecy. But when encrypting, the actual key that you use is very, very important for the quality of the encryption. And we'll take a look at that later at some point as well. What else? Oh, right. Unlike hash functions, because the information content doesn't change, reusing my last example, if we were to encrypt the Bible, the ciphertext would be massive, right? It would be longer, probably. I think it would be longer. It would probably be longer than the content of the Bible because we need it to be reversible. We need it to be able to say, from this random stuff, go back to becoming the Bible. And so we can take a look at that, and I have it in my GitHub as well, but since I have it in front of me, I'm just going to look at it right here. There we go, Symmetric Encryption. So make this a bit smaller. So this is just me importing the crypto library again, and then I just made some functions for encrypting and decrypting. And so it'll be, we're creating the AES-256 cipher that we're using, and we pass in a key, and then we add the plain text to the cipher, and then we output it as a hex string and return it. And that's pretty much it. And then, the reverse in decrypting. But this is, it's built into Node. It's very easy to see. And so if we have a password here, I'll just run that. So encrypted, it looks like 6A415 whatever, but decrypted, it looks like woof, which is in fact what we were passing in. And so you can input whatever, but importantly, like I mentioned, if this were to be longer, then the encrypted text would also be longer, right? Because it needs to retain the informational content so that it can be reversed. That is really the long and short of why I opened that. All right, moving right along to randomness, unless anybody has any questions. So as I mentioned before, this is kind of my, this is the part that I really like. So as it turns out, there's a couple different ways of generating randomness. And you would think that it would be easy, right? You're like, oh, random stuff seems to happen all the time, but not really with computers. And so actually, does anybody have any thoughts on a way of generating randomness in a computer? Like for use in keys and stuff like that?
Using the clock?
Using a clock? So sure, but time is pretty predictable. But yeah, like if you just use the clock at a certain point in time, then somebody else might have to guess. But if they know roughly when you generated it, they could probably, run through. And certainly if you're going down to like microsecond level, but no, time is pretty predictable. But a lot of people do use time, especially in this top one, the RNG. But certainly nobody would use a clock in the cryptographically secure pseudo-random number generator. But good guess.
Does that have something to do with prime numbers?
The prime numbers might be used to add, like to take an initial piece of randomness and make it and extrapolate it, so to produce more, so that you don't have to keep going back to the well, as it were, for randomness. But that's still just math, so it's not really going to. So no, you can't really produce randomness just by using prime numbers. But it's a good guess. But I do believe prime numbers are very much so involved in dealing with randomness and taking an initial random seed and making it longer. No. Can computers be random?
Math.random?
So math.random is a random generator, but it's going down into your computer to fetch that initial random seed. So that's more so the implementation of randomness. but that's still just reading randomness. It's not like generating it, right? It needs to come from somewhere. And the question is, because a computer is inherently a deterministic machine, and I'll give you a little hint right now, when you first buy a computer, it doesn't have anything random in it, right? It doesn't have like, it knows like, this is my database, these are the bits that are in that database, this is my RAM, these are the bits that are in that RAM. There's nothing random in a computer. It's you know like exactly how it works. So the computer actually needs to grab randomness from the outside world, something it cannot control.
How about hardware conditions, like how hot the computer is running?
Yes, that is an excellent source of randomness. It is very hard to predict how warm the computer's CPU is running, for example. So once you generate a couple of once you start up a computer and it gets to do a couple of temperature measurements and stuff like that, that is one of the sources of randomness in computers. And another one is the keystrokes. It's very hard to predict what people will write and how quickly or how slowly, stuff like that. So that's a good source of randomness. The sounds around a computer, although usually people get iffy about turning on your microphone, but theoretically that's not a bad source of randomness either. It's just take those sound waves and digitize them.
When you say keystrokes, does that mean like the keystrokes are saved somewhere in the computer?
Well, the computer certainly listens for your keystrokes because it has to take actions based on them. And so yes, the operating system listens for your keystrokes, and it uses some of those to input randomness. So for example, I believe, don't fact check me too hard on this one, but I believe there was a crypto coin called Zcash. And I believe they bought computers that they never plugged into the internet, and they took them home and they started them, and then they wrote a bunch of stuff on them and, took them in and out of a sauna basically. And then after, like 10 minutes, they were like, okay, we've built up enough randomness in this computer now. It's hardy enough. And then they used it to generate the original handshakes required to start that crypto coin. Yeah, it's a weird world out there. So before those initial couple of minutes can pass on a computer where it can generate its randomness, it is generating this middle one, the PRNG, the pseudo-random number generators, which are not cryptographically secure. So always wait a couple of minutes with a new computer before you do secret shit. All right. So moving later on, we have actually an example of where this can go wrong. So let's go to this one. So this is a link by a researcher, which was very fresh when I first gave this talk. Not fresh now, but he is saying that a cryptocurrency wallet was using Java util random to generate private keys for the users in there. And so let's take a look at why that is a bad idea. So actually we see what is basically the guess we had before, which is also, by the way, everybody always guesses time. So, don't feel too bad. But this random one uses the system's nanotime and takes the seed uniquifier and takes it to the power of it. And the seed uniquifier, we can see, is just a number, really, right? I mean, it's just literally just taking a time and a number and performing math.
Chris,
and that is why.
Could you add a little bit of zoom? Sorry.
Of course. Sorry. No, I should have. It's a good thing you said. Is this better? More?
That's enough. Thank you.
Okay. Right. So it's just doing the time and it's just grabbing the number. And you can even see actually the developer is very helpful here in saying, I'm basing this on Le Écuyer, on his good lattice structures from 1999. Ah, the French. They know their math. But if we scroll up a little bit, or take a look at this, I believe here it says, and I quote, instances of Java util random are not cryptographically secure. Consider instead using this other one called Java security secure random. And this perplexes a lot of people. that there's like different qualities of randomness, if you will. And so a lot of people, because Java util random is what everybody uses when they're learning to code and whatever, they just assume it's actually random. It's not, and nor is math.random. There is cryptographically secure random stuff inside of Node, but math.random is not one of them. You heard it here first. But unfortunately, people usually in languages tend to build kind of the easy version first, and then they add the secure one. And so the easy version always gets the easier names, like math.random or Java util random. And here you have to know that there is this other one that's in Java security, not in util, and it's called secure random. And so that is a CSPRNG, cryptographically secure pseudo-random number generator. So that's bad, right? Because that's a cryptocurrency wallet. So, plenty of people, developers and engineers, make this mistake. And my point with talking to you guys here is that you will not, over my dead body. All right, moving right along. So let's talk a little bit just about the basics of generating randomness. Generating randomness, like it says here, if you have something very small, then it's going to be hard to generate something truly random that matters. So for example, if we're looking at generating randomness, but we're only allowing it to be 2 characters, then there's only 4 possible values that it can have. So we usually call this like the key space of the key space, or said another way, it's the possible values, right? So there's 4 possible values given just 2 bits. Does that make sense? That if all we have is a bit that can be either 0 or 1, and we're only allowing for 2 of them, then there's only 4 possible values that those 2 bits can have together. And this becomes important when you consider if you're using this as a key to encrypt something. For example, using AES-256, using that cipher to encrypt something, my secret message for Alejandro, or Alejo, sorry. Because one, only 4 different possibilities is very easy to guess. And also, you're just not really inserting a lot of randomness into the cipher. And it's kind of like, I don't know quite how to say it, it's like a food processor, right? If good food goes in, then good food comes out. But the same is true for a cipher. If a good key comes in, then a good cryptography comes out, like good encryption comes out. But if a really bad key goes in, then there's nowhere helping you really. And so generating good randomness and having a long key that has a lot of possible values ends up being very important. And so if we take a look, for example, the key space for AES-256 is actually right there in the name. It's simply the AES cipher, but with a key that is 256 bits long. So that's literally what it means. So if you're doing AES-256 or AES-512 or AES-128, the only real difference between all of those is just the key size. And so there's just a little bit of math here. And you can kind of look at that in your own time, if you will, if it's having a hard time penetrating in. But 1 bit has a key space of 2, right? It can only have 2 possible values, 1 or 0. And so if we were to use just a bit, 1 or 0 for AES-256, this is the key that we would have to use, right? It would have to have literally 256 values long if that's what we're using. Certainly, if we allowed each character to be more than just 2 possible values, 0 or 1, then the key would in function be shorter, right? So if we were using hex, for example, hexadecimal notation, then each one could have 16 possible values, and so it would be shorter. But at the end of the day, what we're looking to get is this 2 to the power of 256 possible value, possible different versions of this key, which ends up being 10 to the power of 77 possible combinations. So a lot of possible combinations. This is the very definition of a very, very hard to guess key, right? Nobody's going to be guessing this. And therefore, not even a supercomputer, right? And therefore, the cryptography ends up being very secure. The encryption ends up being very secure. It kind of makes intuitive sense, right? Long keys that have a lot of different possibilities are better than short keys that don't. Okay, so moving right along. Yeah.
Is that the reason why a lot of passwords require at least 8 characters?
Oh, that is so good. You're clairvoyant. That is literally what we're about to get to in like another slide or two. And yes, it is 100%. So, good call. Yeah, literally the next slide. So, this is, as she just mentioned here, this is why a lot of websites try to force you to do different weird passwords, because they're basically offloading that key space entropy requirement onto the end user, right? They're trying to get us to choose more secure passwords. And they're failing horribly, I might add. I mean, again, the most common password in the world is 1, 2, 3, 4, 5, 6. But that's why, and because they want to have different values or whatever, that's why they're like, have some letters, put some symbols in there, add some digits. It's going to be great. And a lot of us feel kind of this false sense of security because we're like, oh, great, they're enforcing strong passwords. Hell, my site even does it. But those passwords are actually like not necessarily that much stronger, actually. Like it'd be better just have like a slightly longer one. Like the length of the password is the only, I would argue, thing that really matters once you have as many letters as are in an alphabet, roughly speaking. So with that, I have another comic for you, and which talks about exactly this. Okay. I believe everybody probably has finished reading it by now, roughly. Anybody still working on it? So the long and short of it is, the point of this is basically to say exactly what we've been saying here before, which is that common website password requirements enforce really bad passwords that are hard to remember, as opposed to good passwords that are easy to remember, unfortunately. And this talks about exactly what we've been going through here with the key size mattering. But in the key in this case is the password of a user. And so big keys are hard to guess. It takes 550 years, whereas shorter keys that have less entropy can be, parsed through very, very quickly. So with that, this is a different way. We're kind of in the home stretch here. So some sites now have actually started making it so that you don't need to have a password at all. Slack does it. Execute program, which is a good, whatever. It's a coding thingy, but they don't require you. They don't even let you pick a password. And so this is basically because, one, humans can't be trusted. Most humans can't be trusted to pick strong passwords. And by the way, I highly recommend using something like 1Password or something like that. And so they just bypass the problem by, saying, I'm just going to email you a link and I'm going to save your session and we're just not even going to worry about it. and we're not going to save any passwords. But that, it makes it a bit more painful to log in, honestly, because it means you have to always go back to your email and copy and paste. So it becomes kind of a hassle, honestly. And it still doesn't save you if somebody breaches your email, but it's actually not the worst idea in the world. And you can already kind of imagine how they probably built this, right? All they do is like make magic link, generate something random, stick it in Redis or whatever, and be like, this user should go to this, should be inputting this random number or whatever, email that out to the user and get it. Email, by definition, isn't very secure, however. And so that's one of the security gripes I have with this method of doing it, because anything you send an email is basically plain text. And so if somebody intercepts it and grabs it, and they could theoretically like steal your account that way. So it's all different kind of login authentication schemes kind of have trade-offs, but this is one that we're seeing more and more of, and so I thought I'd bring it up. We also haven't really mentioned two-factor authentication, which is kind of nice. I mean, all things considered. The problem there is it ends up in causing a bit of a usability strain for a lot of users. It's like, oh, now I have to see this generated code, and it's hard for users to internalize how it works inherently. And so I think that's why we haven't seen even more people adopt it. Like most websites make it optional for that reason, even though it's actually a really good idea. But it causes some usability issues, and so people don't use it as much. But theoretically, with two-factor authentication, your username and your password could leak, and somebody else would still not be able to get in because they'd be on like a different computer or whatever, and they still wouldn't have access to your access code that's on a third-party device or on a device. And so it's actually really like a great way of doing authentication. And so that's kind of like something very common. There's always a struggle between usability and security, right? Perfect security is perfectly possible. It's just very unuser friendly, generally speaking. So, all right, magic links. This was like half the reason I put in this slide. All right, so to recap, never save a password in plain text. Just don't do it. I'll come find you, I swear to God. Hash functions are one directional, and they are the workhorses. I only used one way of doing it right now, or sorry, I only showed you one use case for hash functions. Hash functions are used everywhere. It turns out hashing something in one direction consistently is super useful. Just look at checksums, right? I'm scanning over a bunch of, we're kind of going on the side here, but let's say I'm like scanning through books and I'm looking for, are these books a duplicate of each other or not, right? And I don't want to compare the entire contents of the two books. And so I hash them, and then I just compare the hashes. Ta-da! Hash functions are the best. Unlike hash functions, symmetric and asymmetric encryption, ciphers can be decrypted and encrypted. Good randomness is important. If you're ever implementing something that has security implications, make sure you know where your randomness is coming from for generating your keys and stuff for encryption. And again, if you are a high value user and you're using a bad password, there's really nothing developers can necessarily do. Like there's no surefire solution to fix that. Two-factor authentication is getting pretty close, but if you choose to have a bad password, not have two-factor authentication on for a website and it leaks, that password is probably going to get breached. And you should not be reusing that across many different sites. Because it's gonna get bad and quick. So no matter what the developer has done, they can try to protect you as best they can, but you're probably going to be in trouble. So I highly recommend using password managers. And I think that's pretty much it. Thank you everybody for your time. I'll accept any questions. I am a capstone mentor, so I will also be in the Slack channel, so you can ask me anything there, frankly. I'll upload this keynote to that channel right after this. And I have some further reading resources as well on a lot of this stuff that you can look at if you are interested as well. But that's pretty much what I have for you. Thank you very much.
Thank you.
Thank you.
Thanks.
Thank you. Thank you.
Thank you.
No, don't worry. You don't all have to say thank you.
Oh, hey,
But
Chris,
thank you.
actually, Chris,
Yeah.
actually, I have a little question about the two-factor authentication. I think I heard you say there is like usability issues regarding that. Like I can think of two, like for me personally, I sometimes find it a bit inconvenient. I'm guessing that's one of them. And then another one I can think of will be like sometimes like you'll be sent in text with a code to type in, which I'm thinking one way is like if a person changes their number and they don't have that. Are there like any other user issues with that?
Certainly, yeah. So one thing is, so the big one actually has to do with recovery codes. So when you have a two-factor device, they usually give you recovery codes, and it's very hard to get people to save them. And the reason for this is it's hard for the developers to, if you lose your password and you're trying to like reset it, that's one thing, because then we just affirm that the user still owns their email. But if they like drop their phone, let's say you're generating these like little 6-digit codes on your phone, if you drop that phone down the toilet on Google Authenticator and you don't have recovery codes, there's really no way for you to get back to this point where you could generate those 6-figure codes again. And so then if you haven't saved your recovery codes, you're in a really bad situation, and you end up like sending, you know, passport photos to Google to be like proving who you are beyond a reasonable doubt and stuff like that. So recovery is a big usability issue when it comes to two-factor authentication. But then the one you mentioned is very, very true. Like I have to get my phone, or I have to open some different program on my computer. And actually sending two-factor codes through text is inherently not very secure, because the text messaging system wasn't really built to be secure. And it's very easy for people to steal phone numbers and get your two-factor authentication codes, actually. So given the option between having the codes texted to you and pretty much any other type of delivery, pick the other one if the site is offering both.
Okay.
I have a question
Yeah,
about.
good question. Yeah.
I have a question about biometrics and how it works. Does your biometric data get hashed as well?
Yes, it would. I would assume. I haven't built biometric login myself, but I would assume the same, because you still need to save the signature or password or whatever you want to call it. And I'm actually an identical twin, and so biometrics is not a good idea for some of us.
So I have a follow-up question to that. So if biometrics are basically, let's say, passed or whatever, is there any way for a computer to like loop through, I guess, like fake biometric data, or like fake biometric data in general?
So that it comes down to kind of that's a great question, and I feel like I could be talking about this one for a while, but I'm gonna look at what the job that biometrics is really doing for you, right? It's really replacing the user providing something unique that they only know, something secret, right? And in this case, it's like the blood or a scan of your, you know, face, or your iris of your eye, or a fingerprint, right? Some sort of biometric data. And so certainly pushing a thumb against something for Touch ID, for example, you know, what's actually probably happening behind the scenes is that it's scanning that thumbprint and it's digitizing it, and it's treating that as the source of randomness, right? Of repeatable randomness, or as the password. And so it digitizes that, takes it and hashes it, hopefully, and sticks it in the database. But of course, you know, a fingerprint is a bit iffy, because it's probably not going to be exactly the same every single time. Like, you know, you just touch the fingerprint one way, then another way, and like maybe one day you have a little bit of oil on your hand. Maybe you, like, I don't know, accidentally cut yourself just a little bit. Like, so you can expect that there's going to be some, for certain types of biometrics are always going to be the same exactly, where certain types of biometrics will need to leave a little bit of error margins in there to say, like, this is actually kind of close enough to what we're expecting. And so that's that's a tricky part for a developer. That's like part of the code, is to make it into something that's reproducible and look at, like, is this close enough? Is there a statistically insignificant chance that this is somebody else?
Gotcha. That makes sense.
Yeah.
Thanks.
No worries. Good question.
Hey, I've got a question, something I'm kind of curious about. So actually earlier today, I was resetting a password for an old account I rarely log into. And while resetting the password, it did not allow me to enter certain types of characters. And knowing that we had this going on tonight, it just kind of had me curious about, are they stuck in the past in some kind of way, like using maybe an old system that doesn't take those characters into account, or rather the characters they do allow are limited? Is this something I should be concerned about? I'm just really wondering your thoughts on what that might be.
Absolutely. So it can be a couple of different things. So certainly developer debt is a thing. It's once you've put a system in place, it becomes tricky to sometimes convince the business side of the business to be like, you should really let me update this. And they're like, well, what's the business upside? Well, people can choose stronger passwords. And it's like, well, why do we care about that? And it's like, that's always a struggle with security sometimes. So certainly they could be stuck on old infrastructure. So you could be right about that one. A more common reason for this actually is that they would choose common, they only want it to be common symbols that exist on a lot of keyboards around the world, is another one, which is a little bit in the past as well. But the third one is actually a security issue. So I don't know if you guys have learned anything about like SQL injection and stuff like that, but because these, how should I say, one avenue of attack, not necessarily for a password, but since it's loading this in and running it on your server, certain characters that are kind of earmarked for the programming language can let you like escape strings and run code on the server, or escape your, like as they're being loading into the database, they can like escape their bounds and run database commands. So this is, and so what a lot of developers do is they don't allow certain like databasey type characters, or characters that belong to the programming language of choice, because they're worried that they've messed up somehow, and that and that somebody could maliciously craft a string to run malicious code on their systems. So that's usually why.
That's some great insight. Thank you.
Chris, I know that this is probably bad practice, but I have about 5 passwords that I reuse. What would you recommend?
This is 5 and not 1.
And one of those, so yesterday I got a new laptop and I was setting up with a MacBook. And I was gonna use the password that I had from my older laptop. But since all of this is Mac, it was telling me that my password for my computer cannot be the same as my iCloud password. And I was thinking,
right.
well, like, I was just thinking with what we saw here today, like, if my passwords are hashed, how can they tell that I'm actually using the same password?
So if the passwords are hashed and if they're hashed only and the hashing algorithm is similar, then they can't tell. But usually the risk with reusing passwords isn't necessarily that somebody will break it in the same way across different platforms. It's that they'll break it on one platform, and now that they know your password, they'll just, use that other, they'll just go to other platforms, try to figure out if you're a user on them, and then just retry that password. Right, so that's really the bigger risk with reusing passwords, because different places will usually hash and salt differently if they're following good practices. So and that's a good point, right? It's to prevent like a lateral attack across many different platforms. Is another reason to follow these suggestions that I laid out in this presentation. However, using a couple of different passwords, yes, like technically it's better to have unique passwords. I don't actually know the password for almost anything. I know the password to my 1Password, and then all my other passwords are generated. So like you could torture me to death. I can't tell you any of my passwords. And that's kind of what you want, right? So you don't have to like trust that I'm not going to give it away, so to speak. But if you only have one really strong password in your life, all right, everybody listen up now. If you only have one strong password, make sure it's your email password, okay? Because if they break your email, they can reset all of your other passwords, okay? So, yeah. If you hadn't considered that, I am telling you now, email password should be strong.
I actually have another question. So passwords get hashed, right? And then they get compared. They get compared in the front end or back end, right?
Yeah, in the back end, never in the front end.
So if it's compared in the back end, that means that the server is sending something to authenticate the front end. Is there any way that someone can, like, I guess, intercept that and use that like response universally? Like,
yes. So it's a great question. So what you're basically talking about is session hijacking. So as I attempt to log in, I'm taking my password, I'm sending it to the back end, if we're looking at like a web server, for example, and it's getting hashed there and compared. And if those match, then the server generates a new random string that it says, this is your session token. There's a couple of different ways to do this. There's like JWT and stuff like that. But at the end of the day, it generates some sort of token that it sends to the front end. It says, you can reuse this for 2 hours, 2 days, whatever you want to call it, as your authentication. And if somebody else, sits down at your computer, and what you're basically talking about is kind of like that, but a more high, technology way of doing it. If somebody else sits down at your computer and like opens your web browser and that session is still active, then they can successfully impersonate you. Sure, absolutely. And so if somebody could steal that session, by opening up the developer tools and looking at the cookies or the local storage and just grabbing that session, then they have successfully hijacked your session. The saving grace here is that that is temporary access. So they will only have access for as long as that session is valid, and they still don't know your password. And so they cannot hit any of your other accounts that might be reusing that password.
Gotcha.
So, yeah.
Okay.
I have a question.
All right. Sure.
Last one, sorry. How does something
no worries. We got another 8 minutes.
Okay. How does something like Chrome or LastPass, how do they manage your passwords and data?
Honestly, probably in a very similar way to what I just described. You're saving the, anytime they're saving the password, they also need to put it somewhere secure. And so certainly the operating system might provide some better solutions. I know Apple has like different, like on phones and stuff, they have like secure enclaves, which I'm not super familiar with, where they handle the interaction to try to make sure that anything put in there is very hard for somebody that steals the hardware to take. But roughly speaking, they're probably saving it in largely the same way as a hash with a salt, I would expect. But I don't know that absolutely for sure. Wait, let me think. No, they can't be. Sorry, I retract my statement. They need to show the plain text password. So they cannot be hashing that password because hashing is one directional. It can never be reversed. So they must be symmetrically encrypting the passwords using something like AES-256. So something that can be encrypted and then decrypted. And so when you log on to your 1Password or like when you're unlocking your vault with your master password, I don't know if everybody is familiar with 1Password. I can actually I'll show you mine. This is my 1Password. And so it's like, enter your master password. As you can tell, it's really long. And so that's how I get into my different passwords. and then I can look at, whatever different passwords I might have. But when I'm performing that action of inputting that password, what I'm essentially doing is decrypting the passwords, right? That's really what I'm doing. So it's a symmetric encryption, and I'm decrypting the passwords using my master password. Does that answer your question?
Yes, thank you.
Hi, Chris. I have another question. Oh, shoot, what was I saying? Oh, yeah. Do you know what may be going on in some site systems where, like, you change your password because you have to reset your password because you forgot it, and then it takes it a few hours before it's like registered and you can actually sign in? Because like I've had times where I had to reset my password and I try to type a new password and it doesn't work, and I wait a few hours and then it works.
Actually, I'm not sure I've seen that too often. I mean, it could just be that their emailing system, but I can't imagine a reason why you would have an artificial time limit from trying to reset a person's password. No, I'm sorry. I actually don't know the answer to that one. I haven't
Yeah, I was
seen
just
that.
wondering if it was like a slow system or something. I don't know.
I mean, it probably is a slow system. They're probably like batch sending out their emails and trying to like prevent ending up in people's spam filters. So it could be like ancillary concerns like that. But from a security perspective, there's no real value add in forcing people to wait a bit to reset their passwords, to my knowledge.
Hey, Chris, I have one more question.
Chris.
Sure.
Yeah, no, I have one more.
Putting on the lights so I don't look like such a stalker.
So the question is, it's not password related. It's more so about things like WhatsApp. WhatsApp claimed to be like end-to-end encrypted, and I've always wanted to know what exactly that means and how does encryption work for things like messages.
That is a good question and a big one. So roughly speaking, WhatsApp was built, WhatsApp uses something called a two-ratchet encryption or something like that. And it was built by a guy who has an excellent name, which is why I remember it, but his name is Moxie Marlinspike. And he runs a different company called Signal, which is another encrypted chat interface. It doesn't have as much money backing it as Facebook, so it's a little bit less used, but they just actually did a big raise. But it is pretty much what all truly security-minded people tend to use, is they tend to use the Signal app. Because it also uses that same encryption that they've open sourced. So what does it mean to be end-to-end encrypted? Well, what it really means is that the person who is sending the message, it encrypts on the device you're sending the message from, right? So that's one end, and then it decrypts. It doesn't decrypt until it gets to the device you're sending it to. So if I'm trying to send you a message, Michael, then on my device, it goes to some server, and then it goes down to your device, and your device is the thing that's actually doing the decryption. So it's not the server doing an decryption and then pushing the plain text down to your phone. It's actually end-to-end encrypted, right? That's what that means, is that it goes from device to device. And so it solves the problem of insider threat, where if somebody at WhatsApp wanted to look at the message, they literally can't.
Got it. Thank you.
Yeah. And we can get into like how you do that. Usually you mix asymmetric cryptography with symmetric cryptography. And the reason to do that is because symmetric cryptography is faster. So like the one I showed you with the AES-256, where we were just encrypting a bunch of stuff. Actually, I had it right here. This one is really fast. Oh, wait, I'm not sharing my screen still. Well, yeah, so symmetric cryptography is faster. So usually what you end up doing is you end up wrapping you end up symmetrically encrypting the actual messages going across, and then you just sprinkle on the asymmetric cryptography for the metadata so that it knows where it's supposed to go and stuff like that. And that way you can kind of like selectively decrypt that part on the server, because you can't encrypt the whole thing because you would never know who it's going to. Like you'd never know that I, Chris, am sending something to Michael.
Gotcha. Okay.
So there's always some pieces that you need to be decryptable by the actual server, but end-to-end cryptography is that you encrypt as much as possible the whole way through.
Gotcha. Thank you.
And a lot of companies say they are end-to-end encrypted, but they're not. For example, Zoom, which we're using right now.
Oh, yeah.
And speaking of, Zoom is like, oh God. Zoom apparently uses like there's different modes of running AES 256, and they use something called Electric Codebook, ECB mode, and it is absolute trash. So yeah, nothing we say here is secret at all. I promise you that.
Chris, I got a question for you. If we're thinking that most passwords are getting hacked by a computer and an algorithm that's able to throw out like, 1,000 passwords a minute or a second, why not just write something into your code that says like you can only enter X number of passwords within a minute, and then it locks that, and that throws the whole concept of hitting, this infinite number of passwords in a short period of time right out the window.
Yeah, so that works fine for if you're on a web server. The throttling the amount of attempts is a very common practice, and it's a good idea. And so enforcing more of a time constraint on the actual hashing part just means that even if the database leaked and you could start, because then you can't add any throttling. There's nothing stopping you from attempting a bunch of passwords against the database that you've stolen and loaded onto your computer. And so, but if the action of generating each password before you attempt it still takes 0.1 second, then that still bottlenecks you there, because it means you can only test 10 passwords a second instead of the original 100,000. So it just reduces your attempts by a lot. So you're right, throttling on the web server is a good idea and is a very common practice.
Thank you.
Chris, I have a question. Sorry. So you mentioned a few times about like 1Password. So using 1Password, is there a risk that if 1Password itself will be hacked, so basically they will have all your passwords for everything?
Yes. It depends on where the encrypted passwords are stored. Like if it's pushing it out to the server, I have looked into 1Password quite deeply because I'm interested. I am who I am, and their security practices are very, very good. But at the end of the day, yes, like it's kind of like trusting your doctor, right? It's like, am I better off treating this coronavirus myself, or should I trust my doctor to do what's best for me? And like if you have a really, if your doctor has a serious drug problem and a bunch of debt that they need to pay off, then maybe they don't have my, best interests in mind. And so, yeah, it comes down to, does trusting them put you in a better position than you were in before? And I would definitely argue that for 99% of people, probably yes. That using it is worth it, because very few, I don't think that many people are trying to hack the 1Password servers to get password data, because most people that have looked at how they built their system know that it's pretty much impenetrable. Famous last words, of course. But if you really look at it, most hackers are going for low-hanging fruit. They're going for the common password.
Too much work, yeah, you mean?
Yeah, they're going for like the low-hanging fruit. They don't need to do this bond stuff, right? The only reason to do that is if you have a very specific target in mind. The vast majority of people are just looking to make a quick buck, and so a database leaks online. They look for the common password. Maybe they can do a little bit of ransom. Maybe they can, I don't know, like force some people to do some ATM stuff because you stole their account to their Vanguard, something like that. But they're not really looking to. Maybe they can do a little bit of identity fraud, but that's about it.
Okay, I see. Thank you.
Yeah, which is a much lower bar. Great question, but it's a much lower bar than going after the cryptographic security of a encrypted password vault on 1Password.
I have a quick question. Sorry, I have a question more so as to the comic that you had, the last comic that you showed. Why are passphrases not really more commonly adopted in the security industry? Like, it would seem that it would be easier to have like passphrases that have longer like longer lengths and they're easier to remember, as opposed to what we have now currently, which is, you try to make a short password that's very complex?
I honestly don't quite know. And I should mention, by the way, that, given we've come up to time, I won't feel bad if anybody decides to peace out. I mean, I'm not your instructor. You don't have to be here, by the way. But thank you for participating. But so just to answer the question, I don't know why more people don't recommend those types of things. You're starting to see more like password strength indicators, and they will show that longer passwords are kind of part of what's stronger. But it's very hard to actually look at people's passwords and define whether they're strong or not. Like the only way to really do it is to use like an open API and be like, is this the password somebody else is using? And if it is, because there's an API actually that's built by this guy, Troy Hunt, and he built the Have I Been Owned website, which I highly recommend because it'll show you whether or not your email has been leaked or not. Actually, I can just show it maybe. Let's see. But you could use that one. Let's see here. Have I been owned?
You mean?
So this is the Have I Been Owned? I know I have been. There we go. So I was a part of the Bitly breach, the Town of Salem breach, the Bitcoin breach, 2 unclear ones, 1 from Discus, 1 from the Dropbox breach, 1 from the LinkedIn breach, StreetEasy breach, Ticketfly. I swear to God, I'm not even on Ticketfly. So there you go. So thank God I'm not reusing those passwords. But they also have a passwords API that you can actually use. And you can use that to actually look up whether a password has been a part of the breach. And then you can tell people, hey, that password you're trying to use, you think it's a unique special snowflake, but it turns out like it's been a part of 10 breaches so far already. So it's probably not a very good password.
Chris, thank you very much for coming. Thank you everyone that participated. This is a I've seen this talk for a few times and I always get something new. So
I'm glad you keep coming back, man.
Absolutely.
You muted yourself.
Oh, sorry. Can we get the claps for Chris and the reactions here in Zoom? There we go. Thank you, everyone. Thank you, Chris. Everyone have a good night. I think I recorded. I'm gonna be sharing the recording. Chris, I hope you don't mind. On Slack, so you can view it after.
Totally fine. I'll upload my my presentation right now as well. All right. Have a good one, everyone. Thank you so much, and hope you learned something.
Thank you very much.
Bye. Thank you, everyone.